Hello and welcome to Physical Attraction. This episode is called NIF-ty Business. The National Ignition Facility at the Lawrence Livermore Laboratory in California is the largest laser device yet constructed in the world. It represents perhaps the most instantaneously powerful human invention on Earth. When its beam fires for a few picoseconds or millionths of a second, it irradiates its target with 500 terawatts of power. By comparison, the entire human race currently consumes on average around 13 terawatts of power in the form of primary fuel consumption from fossil fuels, nuclear and renewables. In other words, it's as if all the energy use currently going on everywhere in the world were multiplied by 30 and then, for an infinitesimal moment, blasted at a tiny capsule of fusion fuel in an attempt to ignite a fusion reaction. This week we're going to talk about how this device was built, how it works, and what it managed to achieve, and perhaps get on to what it failed to achieve. It's worth pointing out, of course, that right from the beginning, NIF wasn't just an inertial fusion device. In fact, to many, particularly some of those who funded it, its purpose wasn't really to develop clean, limitless nuclear energy and all that jazz. Instead, this was really about nuclear weapons. We've described before how inertial confinement fusion with lasers is, in essence, trying to create the smallest possible hydrogen bomb that you can make. After all, the principle of getting hydrogen nuclei to fuse by rapidly compressing them had already been demonstrated in H-bombs around the world. The problem was doing so in a controlled way that might allow you to harness the energy for peaceful purposes. In the early 1990s, the world's superpowers were negotiating to stop nuclear testing altogether. From the era of Reagan and Gorbachev, the aim was to prevent nuclear weapons testing from taking place in the future. The Comprehensive Test Ban Treaty, eventually signed in 1996 after the Cold War had ended, had been the most successful. India and Pakistan both tested nuclear weapons in 1998, and North Korea as a rogue state has carried out a series of nuclear tests in recent years, but compared to what was done during the Cold War, this is small potatoes. During the Cold War, the US alone carried out an astonishing 1,054 nuclear tests, including explosions underwater, crashing planes carrying nukes to see if they'd go off. They launched nuclear weapons thousands of miles into the atmosphere to see if they could create signal-jamming radiation belts. Edward Teller engaged in some beloved underground explosions to test the use of nukes for civil engineering purposes, and so on. The fact that the US has not had a single nuclear test since 1992 is therefore, by contrast, something of an achievement of the Test Ban Treaty. But this Test Ban Treaty, while an achievement for peace, did present US national security hawks with a problem. Not only could they not rely on any new designs of nuclear weapons, which could no longer be tested, but they also couldn't be sure that the existing arsenal would continue to work. After all, like any mechanical device, nuclear bombs can rust, and they also contain radioactive materials that decay over time. Without a great deal of data on how nuclear weapons age, it's difficult to mothball them, come back in a century, and be sure that they'll still work. And of course, in the mad world of nuclear theory, this could weaken your deterrent or your ability to massacre millions of innocent civilians at the push of a button. Imagine if, for example, your adversary knew that your nuclear weapons stockpile was aging and unreliable without testing. That throws off mutually assured destruction, and you may no longer have the horrible Pax Atomica that we all live under. So something called the Science-Based Stockpile Stewardship Program was initiated, that would use fancy scientific testing to ensure that, yes, don't worry, Armageddon was still only an irate president or a false alarm away. The big question you're probably asking is, how does NIF fit into this? Well, the precise answer to that, as you might expect from any project that involves billions of dollars of scientific funding, is a little controversial. It's easy to see why having scientists study the nuclear weapons for signs of decay, occasionally replace the plutonium cores or maintain the stockpile with new weapons, and examine the response of the materials to radiation exposure would be good weapons stewardship. But how does creating what is essentially the smallest possible nuclear explosion help you to confirm that your current weapons still work well? Surely you could just build new ones. Some scientists even at the time said that the device was, quote, worthless, it can't be used to maintain the stockpile, period. And the truth is that, if your aim was really to maintain the weapons stockpile, NIF would not really represent good value for money. For a start, although thousands of weapons, some of them many decades old, have been examined, few defects have yet been found, and many could be corrected simply by replacing components. The scientists argued that NIF was the only place on Earth that could create nuclear weapons-like conditions without detonating nuclear weapons. And they argue that, quote, the ability to study the behaviour of matter and the transfer of energy and radiation under these conditions is key to understanding the basic physics of nuclear weapons and predicting their performance without underground nuclear testing. Well, that's all well and good, but is it really necessary? After all, you know the weapons work. They don't need to be tested anymore. They just need to be maintained and their condition monitored. You don't need a giant laser to do that. But what you do need a giant laser to do, as the scientists said to Congress, is to, quote, train and retain expertise in weapons science and nuclear engineering without the need for further underground tests. In other words, behind the thin veneer of maintaining the stockpile, NIF sold itself to Congress as a weapons research facility that would stop just short of actually blowing up nuclear weapons, the closest thing you could get to a nuclear testing program without the nuclear testing. If the US ever decides, for whatever reason, that it wants to start designing new kinds of nuclear weapons, the scientists, science and expertise developed at NIF will be used for that purpose. People called this out at the time, especially in the magnetic confinement fusion community, who were smarting from budget cuts in the US. A good example is Tom Kalina's 1997 article in MIT Tech Review, but ultimately their protestations didn't matter. The weapons enthusiasts would get their weapons facility, and the laser fusion enthusiasts would get their biggest ever device. You will of course remember from previous episodes that laser fusion has been tried a number of times before, in devices like NOVA and Shiva. While the scientists' understanding of how to control and manipulate powerful lasers had advanced significantly since those earlier devices, they were no longer burning holes in their optical equipment so much, for example, like their magnetic confinement fusion friends, they were discovering endlessly brand new ways that plasmas could refuse to behave. Instabilities like the Rayleigh-Taylor instability meant that tiny deviations from uniform irradiation resulted in bumps in the plasma, which quickly grew, eventually growing and becoming larger, bursting out from the plasma, carrying away energy before ignition could be reached. Hot electrons carried away the energy that was supplied to the fuel, preventing the nuclei from getting hot enough to overcome their electrostatic repulsion and fuse together. The NOVA and Shiva projects therefore advanced our understanding of how this might work, but ultimately failed to achieve break-even. NIF followed the standard, perhaps inevitable approach that you're expecting now for a new nuclear fusion device. It promised to be 10 times bigger than its predecessor and correct all of the problems through sheer brute force, delivering 10 times as much power. Uniform irradiation would be achieved using 192 separate beamlines, each focusing its laser pulse on a separate fraction of the sphere. The Shiva device, with 20 beamlines, had been named after the four-armed Hindu god. In that sense, NIF was Shiva on speed. Naturally, making a device 10 times larger than NOVA, which had already cost $200 million, entailed a hike in budget. In the early 1990s, when NIF was first hypothesized and designed, the initial projections for its budget suggested a cost of around $600 million to build the device. As we shall see, this turned out to be yet another example of one of these budgets that was a horrifying underestimate. Making a device with this level of precision is extremely complicated. First off, as we've described before, the whole point of symmetrically irradiating the fuel capsule is to avoid instabilities. You need to create a spherical shock wave that will symmetrically compress the fuel capsule, heating and compressing its interior to astonishingly high densities and temperatures, for that inner segment of fuel to ignite and, hopefully, lead to a chain reaction that burns the rest of the pellet with fusion reactions before it's blown outwards again. This means that every one of those 192 beamlines needs to be as close to identical as humanly possible. Otherwise you'll get instabilities that will arise from whichever one is misaligned, or firing slightly too slowly, or firing with the wrong amount of energy, or delivering the wrong amount of heat, or a few billionths of a second out of step with the others. So you need to make sure that these beams are as coherent as you can imagine them being. There are an incredible number of things that can go wrong with this sort of device. To give you an idea, let's briefly go over its design. First, there is a single central flash of laser light from a single coherent source. This is then split into 48 separate beams which pass through pre-amplifier modules. They enter a laser cavity where the beams bounce back and forth through an illuminated crystal, picking up energy as the atoms of the crystal vibrate. Here they're amplified from nanojoules to millijoules. Then the lasers pass through a circuit 4 times, picking up more energy as they pass through yet another crystal filled with laser material, which causes the release of yet more photons as the lasers stimulate and excite the atoms in the crystal. This boosts them to around 6 joules. Then they pass through the main amplifier. This is essentially another crystal which is illuminated with rapid flashes of light. This excites the electrons in the crystal into higher energy states. When the laser passes through, it triggers the decay of these excited states and the release of yet more photons, amplifying the laser pulses to a brief but powerful state that has around 4 megajoules of energy. For comparison purposes, the laser now holds about as much energy as you'd get from exploding a kilogram of TNT, or the kinetic energy of half a dozen cars speeding down the motorway. Then you have the spatial filtering stage, where the lasers pass through a series of filters to ensure that they remain in very sharp focus. After this point, The beams are then directed towards the target chamber, which is a steel sphere around 10 meters in diameter. But before they can get there, frequency conversion has to take place. The lasers used, predominantly the famous neodymium crystals which do such a good job as laser materials, produce very monochromatic light at infrared frequencies with a wavelength of around 1000 nanometers, just outside the human visible range. But infrared light is, unfortunately, extremely good at heating up those undesirable hot electrons that we've talked about in previous episodes. Remember, these are the ones that absorb the energy that's supposed to go to the nuclei and then ricochet around and ruin the compression of the core. So they have to change the frequency to make it couple more strongly to the nuclei rather than the electrons, so that more energy is passed to the nuclei for fusion to occur. So some thin sheets of potassium dihydrogen phosphate are put in line of the beam. These effectively double the frequency of the photons, halving the wavelength. Explaining precisely how this works is pretty difficult, but essentially what happens is the illuminating laser light interacts with the crystal itself, which produces a polarization in the crystal where negative and positive charges in the crystal are forced apart. As the light passes through the crystal, like a wave, this polarization also waves through the crystal. It oscillates, and it actually produces its own electromagnetic wave at double the frequency of the initial laser light. The first laser reduces the light's wavelength from around 1000 nanometers to around 500, and then the second laser recombines some of the 500 and the 1000 nanometer light through interference to produce light with a wavelength of around 350 nanometers in the ultraviolet range. By doing this, you inevitably lose some of the input energy, around half in most of NIF's experiments, but since you're no longer strongly coupling to those hot electrons, you have a much better chance of producing fusion in the capsule. The lack of good materials for producing UV lasers and the tendency of this high-frequency light to burn through certain crystals are part of why this has to be done. And in fact, even for the short fraction of beam length where this UV light is used, it's necessary to constantly replace the optical components every 50 to 100 shots, which adds more expense to the project as a whole. Therefore, basically, you want to do this frequency change right at the end so that your UV light doesn't have too much time to muck up all of the stuff in your system. Finally, after all of this, the lasers are focused onto the target, which for NIF was usually a pellet of deuterium-tritium fuel around the size of a ball bearing in a gold hologram capsule around the size of your fingernail. In total, each of these beams travels around 1.5 kilometers to hit a target the size of your fingernail. So as you can probably see, a lot of things can go wrong. And unfortunately, all kinds of crazy things did start to go wrong, as Charles Safer lists quite wonderfully in his Sun in a Bottle book. Mammoth bones were found when they were excavating the site, which slowed down construction. The head of NIF was forced to resign when it turned out that he'd never actually earned his PhD, although he had been an established scientist for some years. Other problems were more costly. For example, if there was a tiny speck of dust on the laser glass itself, it would instantly burst into flame when the laser was fired, which would in turn damage the glass. Laser components therefore had to be assembled in extremely clean rooms, then carried around in robotic trucks with extremely clean interiors, something which multiplied the cost of manufacturing the laser. The main amplifier is powered by a huge bank of capacitors that store charge, and they can store 422 megajoules of energy for quick release and supply to the laser, in a similar way to those charge rotating flywheels we talked about for energy storage at JET. But these capacitors had a nasty habit of exploding during construction. They eventually needed to shield them from the rest of the device using steel barriers in case they did explode. Even manufacturing the fuel pellets is incredibly difficult. The fuel pellet is around 1mm in size, but in order to avoid those nasty bumpy Rayleigh-Taylor instabilities, you can't have any deviation on its surface of more than around 50 nanometers. I thought for a while to try and come up with an analogy for this, and it's a lot like this. Imagine you have a sphere around the size of a car. It can't have a single grain of sand on it. That's how smooth it has to be. You get the picture of how smooth this target has to be if you imagine a sphere the size of a car, which can't have a bump the size of a single grain of sand. It's so smooth we can't even conceive of it. And you get a picture of how smooth the target has to be, and manufacturing something that's that small, made of the materials that you want, that's that smooth, is extremely difficult. The initial projected cost might have been around $1 billion, and the initial aim was to finish the project in 2003, after the first ground was broken on the site in 1997. But it will come as no surprise to anyone with even a passing familiarity with complex government-funded projects, let alone those with science as complicated as NIF, regions that we haven't even looked into before, and requiring entirely new technological innovations to be developed, that both the budget and the time turned out to be severe underestimates. By 1999 to 2000, it turned out that basically they could no longer justify the budget and timeline estimates. They clearly weren't going to fly, and there were several independent audits that came along and essentially re-baselined the project, suggesting that it would cost more like $5 billion and it would need to be ready by more like 2008. As in other projects of its kind, some of the management would dismiss for making misleading statements to government officials about its progress. But call it sunk cost fallacy if you will, the project was not abandoned at this point, although it drew on more funding from the weapons stockpile coffers, making it even more military in focus. After all, you have to pay back the military who funded your project. In 2003, the first lasers were fired at NIF, in just one of its 192 beamlines, and by 2009 the project was finally officially completed. The site was dedicated in May 2009 at a ceremony attended by many thousands of people, including the Terminator himself, who was governor of California at the time, and the first scientific experiments began in June 2009. Sometimes, after major fusion devices fail to achieve ignition, the PR machine whirs into gear and says, well, the aim wasn't really to make this one achieve ignition, it was really about learning the fundamental science that will allow the next device to work. Unfortunately, those at NIF can't really make that claim so easily, because they refer to their device as the National Ignition Facility, and the main set of science experiments as the National Ignition Campaign. During the opening ceremony, a banner was unfurled, bringing star power to Earth. Now we finally got here to a bit of history I remember. I read articles about NIF in 2009 and 2010 when it was first switched on, and was excited by the prospect of fusion via giant death ray, as any nerdy teenager would be. And this was at the bottom of the economic crash, and just as fears around climate change were becoming more and more mainstream. So there was a good deal of hype and interest in this device. Even the more sceptical popular science articles published at the time described the task of achieving ignition as daunting, and argued that it might take a year or two, and perhaps had a 50-50 chance of success. The scientists themselves, of course, were willing to be more cautious, and after all, which fusion scientist really wants to promise unambiguously that their device will do exactly as it was supposed to? For example, quote, I personally think it's going to be a close call, said William Happer to the New York Times. He was a physicist at Princeton University who directed federal energy research for the first President George Bush. It's a very complicated system and you're dependent on many things working right. Dr. Happer said that a big issue for NIF was achieving needed symmetries at minute scales. There's plenty of room, he said, for nasty surprises. Next episode, we will look at exactly what those nasty surprises were. Thank you for listening to this episode of Physical Attraction. As ever, you can find us on the web at www.physicspodcast.com, where you'll find the contact form, the PayPal, the Patreon, all ways to get in touch with us and tell us what you think of the show, comments, questions, ideas for future shows. You can donate to the show via the PayPal or the Patreon. Doing either of those will get you access to some bonus episodes if you email me about them. And the best thing you can do if you don't want to do any of that stuff is, as ever, tell as many people as you can about the show. Leave us a review on iTunes, Stitcher, wherever you listen to the podcasts. And until next time then, take care.